Hi, my name is Harry Oosterhuis. I'm an assistant professor at the Radboud University in Nijmegen, and you're looking at the short paper presentation for the SIGIR 2022 conference for the paper Learning to Rank at the Speed of Sampling, Plackett-Luce Gradient Estimation with Minimal Computational Complexity. What I've done in this paper is I've introduced a new algorithm that estimates Plackett-Luce ranking model gradients with minimal computational complexity. What I mean by that is that it's bounded by the underlying sorting algorithm. So the complexity is no longer about the method, it's just about how long it takes to sort, which I would argue is a lower bound on what's possible in respect to computational complexity. This is a follow-up on a paper from last year's SIGIR, where I introduced the first algorithms to efficiently approximate the gradient of a Plackett-Luce ranking model. What you're seeing on screen is a conclusion from that paper, a quick way to compute this gradient. What's important right now is that the gradient here is the complexity of n, the number of samples. You need to sample rankings to do the approximation. D, the number of documents that we're ranking. And K, the length of our ranking. So for instance, a top 5 ranking, a top 100 ranking, that would be the K value that varies there. And I don't have time to go into detail about exactly what's going on here. You see at the bottom of the screen a reference to the paper which explains this further. In this paper, we introduce the novel PL-rank3 algorithm. It actually computes the same approximation as you saw on the previous slide, but the crucial difference here is that we have a much better complexity. So the complexity now is n, the number of samples, times d, the number of documents that we're ranking, plus k, the cutoff length of the ranking, where previously we had d times k. So if you don't have a cutoff, the previous algorithm would have a quadratic complexity, whereas here we're still in a linear complexity. I have to add here that this complexity is only the case given that you have n sampled rankings. So you still have the complexity of sampling that you also have to deal with. How does the algorithm do this? Well, the crucial point here is that we use this following property. So when we sum over probabilities of placement, we can actually rewrite that to the score for a single document and this constant here, which is only determined by the ranking in the rank. And the key insight here is that we compute that second part for the entire ranking beforehand instead of recomputing it for each document. So we define 3 new vectors of size k, PR, DR, and RI, which enables this new formulation that you see on screen here, where we formulate the same gradient, but we're avoiding any summation over k. A nice thing about these vectors is that given a ranking, we can compute them in linear time. The complexity is just k. So we just need a single iteration over the ranking, and we can have these values. That means that to get the full approximation, we can first iterate over k, and then we only have to iterate over d for each of the rankings, which gives us this complexity. Of course, we can only do this after we already have the sampled rankings, so we still have the complexity of sampling that we also have to deal with. For our experiments, we looked at how many minutes it takes to complete an epoch for different values of k on 3 different data sets. And what you can clearly see is that as k increases, the amount of time it takes to compute an epoch explodes as well. So with these old methods, if you're doing a top 100 ranking, this really takes way too long than practically feasible. In comparison, if we look for the red or the orange lines here, which are our methods, we barely see them increase. We have a table in the paper where you can see the more precise numbers, but the key point here is that it does not blow up. So we can really easily go to cutoff 100 without having to deal with these massive epoch times. To conclude this short presentation, I wanted to give this overview of learning to rank methods and the different properties that they have. The paper, the slides, this video you're watching right now, and the code are all available on my website. So if you want to continue this work or get more of an insight, please check it out. Thank you very much for watching.